Right, this video is the level, scholarship 2019 question 4. Right, I hope we can see that. A string given a constant small amplitude by a vibrator of fixed frequency F has a third harmonic wave established when under tension mg is shown set up above. Explain how a standing wave forms with this experimental arrangement. So I'll just talk through what type of question this is, what are the pitfalls, and what are things you got to pick out on. So the first thing that you need to pick up on is fixed frequency vibrator. Typically, all your standing wave stuff that you're taught in level 3, the velocity is fixed. In this case, the frequency is fixed. The only time I've ever sort of come across similar question, I think was a 2018 exam, the NCEA exam, the one I actually marked that exam. They had a fixed frequency generator that had a Kunditz tube, just like tiny dust balls inside of a tube, and the frequency was fixed, but you couldn't change the velocity in that. Here we can change the velocity by changing the tension. So I'll just pause, write the answer for this, and then explain. Right, so I've said the fixed vibrator generates a traveling wave. The wave travels to the pulley, so this side here, which acts as a fixed end. The wave reflects back and changes phase, so that means it's a 180 degree flip. So it flips around because it's a fixed end. If it wasn't a fixed end, there'd be no phase change, it'd just be pure reflection. This reflected wave interferes with the incoming wave constructively and destructively. I've added at fixed positions because I obviously looked at the answers just to make sure I got 100% right, creating the standing wave form. There are other ways to answer similar questions like these. Things you need to consider are the frequency. Because it's a frequency, it's a fixed frequency, it's sending down that wave down the line, reflecting back. The amplitude will be the same pretty much. Okay, in real life it'll decay a bit as it goes along, but in Fantasyland, the amplitude is going to be the same, the frequency is going to be the same, which means the wavelength is going to be the same. In other situations, such as two waves coming into each other, like sound waves or something like that, you need to state that in order for a standing wave to form, the amplitudes need to be the same, the wavelengths, aka or the frequency, you can say either or, because assuming they're going through the same medium, they need to be the same. I haven't put that here, just because I don't think I feel like it's implied. It's implied with the pulley, it's implied the fact that it's fixed frequency. Anyway, next question. Speed of the wave on a string is given by the relationship velocity equals square root tension over mass per unit length, so mu. Show that tension is given by the following expression that, this is mostly just rearrangement really. So we'll rearrange for tension for a start. So we'll go V squared is equal to tension over the mass per unit length. In other words, tension is equal to times both sides by mass per unit length, mu, and that is V squared. I need to make my V's less like U's and more like V's. And we remember from the wave equation, V equals F lambda, so frequency times wavelength, and that is mu, and then I'm going to substitute in this here for V squared, and you can see pretty quickly I get F squared lambda squared. That's a pretty easy question for scholarship. Right, show that this expression for the tension is dimensionally correct. This comes under a subset of physics called dimensional analysis. Every so often they have questions like this here. It's quite an interesting topic. There's some pretty good videos on proofing different formulas, even in math, using dimensional analysis, which is pretty cool. But anyway, so what we're going to do is we're going to show that tension, which is a force, so it's measured in newtons, is equal to, and what I'm going to do now is I'm going to substitute in all the units for each value. So mass per unit length just literally means mass, which is kilograms, kg, divided by length is always this SI unit for length is meters, so mass per unit length. So unit meaning just it's unitless, so it's just going to be meters. Kg per meters, could have been kg per, I don't know what other, it's just going to be meters. Anyway, frequency is just hertz, but really it's cycles per second, so it's per second. In other words, 1 squared, which is just 1, divided by second squared, because we're squaring frequency. And then wavelength is just a measure of distance, which is just meters. And because it's wavelength squared, we get meters squared. And now you can see that I can probably cancel some stuff and move some stuff around. So I'll cancel this m down the bottom here, and that'll get rid of the one up top. So I'll get kg times meters per second squared. And you'll notice that this is just equal to mass times acceleration, acceleration, which equals force, which equals newtons. I think that's really all you need to do. You just need to show that it is dimensionally correct using words and possibly symbols and demonstrate your understanding. Right. Okay, a fan now blows a breeze against a hanging mass, so this mass over here. So the mass is somewhere out to the horizontal. So either way, we'll put it over here somewhere. Near here is my mass. And horizontal, the standing wave changes under these conditions to the second harmonic. What was it originally? It was the third harmonic. So we've gone, chuck in here, from, I'll just call this, we were at F3, third harmonic. Yes. So F3 to F2. And if you know anything about harmonics, if you, like, from the fundamental, the second harmonic is double the fundamental frequency. The third harmonic is triple the fundamental frequency. So from here to here, it would be 3/2, because you divide by whatever this harmonic is and then times to get to the next one. But I don't know, well, I've already done this question, obviously. You can go around in circles with this one here, but you will eventually get there. The other way to think about it is, so we'll just pause here. So draw a quick free body diagram. We're still going to have mg, and that'll be equal to the vertical component of support for this tension and this is just ft here. So now you look at here, you got mg, you got ft, and you'll remember from circulation, or if you have conical pendulums that go around in circles, ft is going to be bigger than mg because it's providing a horizontal component and a vertical component, because it's not obviously falling, it's just been pushed to the side. So we would expect our new tension force to be greater than the old tension force. So what we're going to have to do is we have to find some formula that relates the old tension force to the new tension force. And we've already got the formula for tension. There's literally T equals mu, and then this is where it gets a bit funky. F is fixed frequency vibrator. This is what threw me off initially. I didn't pick up on it until I got to the end. I was thinking, this is a bit strange, what's going on here? It's fixed frequency. So this is what will throw kids off. So this is just fixed, you just leave it as F. So the frequency is not actually changing. So this is not true. So it's a good way to start though, but it's not true. So we got F, and now we got, what do we got, F squared? Yeah, we got F squared, and we got lambda 2 squared. Because this is, hold on, we're going to go lambda 3. So this is going to be the third harmonic squared. So this is a tension for the third harmonic. So this is going to be, and this is equal to third harmonic tension. I'm just writing it so you guys know why I'm doing what I'm doing. And we remember from, I don't know, like, go over to here, third harmonic, it is, we'll write it here actually. So we can fit how many waves? 1.5, so 3/2 lambda fits into the length. And then when we try and, like, that is equal to lambda 2. I hope that kind of makes sense. So this is lambda 3. So this is the third harmonic. 3/, so you can fit 1.5 waves into the length. So I've said I can fit 1.5, well, it's just 3/2, 1.5 waves inside the length, and the second harmonic just fits 1 wave. Because when you drop down a harmonic, you drop down like a half wave because it's a fixed. So now we have an expression for the second, like relating the wavelengths of the second and the third harmonic. So what we're going to do is we're going to substitute them in. So T3 is equal to mu f squared lambda 3 squared, which is equal to mu f squared. But instead of, I can't say it's equal to lambda 2 because that's not true. Then these things wouldn't be the same. But if I substitute in, like I'm trying to relate them to each other, so I will substitute. In fact, I'll leave it in there actually. No, I won't, because this isn't true. I'll just put T3 is equal to, and I'm going to substitute this here in for that. So I'm going to get mu f squared, and now I know my new like wavelength, so this is T2, not T3. Oops. So T2, the tension, is equal to bracket 3 over 2 lambda 3 bracket squared. Now this would have been, if I just put T2, this was just T2, this would have just been like tension 2, this would have been lambda 2, and I've substituted in the fact that lambda 2 is equal to 3 over 2 lambda 3, and that is equal to, pull the fraction out the front, so it's 9 over 4 mu f squared lambda 3, and that is equal to mu, what do we got, f squared lambda, and that's squared as well, lambda 2 squared. So now we can say, and this here is T2. So this is the tension 2. So we can say that T2, hold on, yes, T2 is equal to 9 over 4 T3. There we go. I feel like I've made a mistake with this. In fact, I shouldn't really have that there. Right. In trying to explain it, I've done a whole lot of unnecessary steps I wouldn't have normally done. This is a simple question where I would have just skipped straight to the end. Anyway, explain using examples of physical phenomenon how light demonstrates both wave-like and particle-like behaviors. I'll just pause and write it out and then explain. Right, so I'll just read out what I said. I said, when light is sent through a double slit with slit separation and hole size slightly larger than the wavelength of light, we observe interference. This is a bit of a cat and mouse thing, because if you didn't know what light was a wave, you would know the wavelength needed to be slightly larger than the hole size and the slit. In the answers, talks about diffraction, but I mean, you could have talked about diffraction. I would argue this is slightly more, this explanation is used more often. Because if light was a particle, no interference pattern would be expected. You'd just see dots on the screen where one particle would go through and then hit. There would be no interference pattern, even if you send the light, if you could do like photons at a time. When light is shone on a metal surface, sometimes electrons can be emitted. So I've opened it up with just the photoelectric effect. Whether an electron is ejected, I should have used ejected, emitted, same thing, depends entirely on the frequency of the light, which suggests frequency is proportional to energy. I don't know whether they discovered the energy levels before the photoelectric effect, possibly not, or maybe they use that to confirm the energy levels. I think they might have actually. If you increase the intensity of the light, there is no effect on the kinetic energy of the ejected electrons, which suggests that the interaction between light and electrons is quantized. And what I've said is, i.e. only one photon at a time can interact with the electron. Thus, a particle-like behavior can be inferred. This is a really hard thing to try and gain from textbooks. You've sort of got to come to your conclusion yourself. Because I thought about this question quite deeply, thinking, how could I explain it to students without doing a poor explanation and without getting into the math of it? Because a lot of times you just get lost in the math. It doesn't mean anything. Because you can derive all of this without really getting into the explanation. But what it means is, if you increase your intensity, it really means that the electrons can only sort of interact with one sort of photon at a time, which implies the photons must have some sort of quantization about them. They must, when I say quantization, like units, they can't just be a broad thing of energy. They're like a set thing. Doesn't mean they're a particle. doesn't mean that at all. It just means they have particle-like behavior. So when you learn this, they're not actually particles, and they're not really actually waves. Later on, you learn about, if you do uni, you learn about probability amplitudes and stuff like that there. And I think that's Feynman's approach. But anyway, so hopefully this is semi-clear, and yeah.